Hello and welcome back to Math and Tea, the show where we talk math and drink tea. I'm your host, Professor Joseph Van High, and today I want to start a new series of videos in which I discuss mathematical cryptography. Now, why mathematical cryptography, you might ask? Well, I chose this because it's probably the single most common application of modern mathematics out there. You might even be using it right now to watch this video. Without mathematical cryptography, a lot of the things we take for granted about the internet and how it works would just simply, well, not work. Now, before we get too carried away, let's talk about cryptography in general before we start talking about why we bring mathematics into it. So, in general, when one talks about cryptography, one has two people, Alice and Bob. No, I didn't make those up, that's what they're typically called. Anyways, Alice and Bob want to share a message. So let's say Alice here wants to send a message to Bob. Alice has a message, which is typically referred to as plain text. She encrypts this using some sort of encryption function. This results in ciphertext. Alice then sends the ciphertext to Bob. Now Bob has the ciphertext and now decrypts it by using the inverse of the encryption function. This results in Bob getting the plain text back. Now, it really wouldn't make sense to use cryptography if only Alice and Bob are involved. So there's a third party, an eavesdropper, who is normally called Eve. Okay, so we have Alice and we have Bob, and then we have Eve. And Eve can see everything that's being sent between Alice and Bob. In particular, Eve knows the ciphertext. And the whole idea of encryption is to try and prevent Eve from being able to decrypt that ciphertext and read the original message. Now, there are ways that Alice and Bob can communicate that are functionally unbreakable. This is the case with the OTP, or one-time pad. In a one-time pad, basically Eve has no chance, there's just none. However, there's a lot of setup needed to use a one-time pad. Alice and Bob already need to have been able to communicate the one-time pad function in secret, in private, before they decide to send the encoded message later where Eve can listen to it. And worse still, it's called a one-time pad for a reason. Use it twice and Eve can start to break it. So every time that Alice and Bob want to communicate in a way where someone can listen in, they already have to have communicated in private as to how they're encoding. In cases where you just need that level of security, well, one-time pads might be worth it. But in general, it's just not feasible. So let's consider a slightly different scenario. Let's say I want to buy a book. It's a good book. Anyways, let's say I want to buy this from some online distributor, like say Barnes & Noble or Amazon or something like that. So I have to tell them all of my credit card information. Needless to say, I want to encrypt my credit card data. So me and the bookseller work out some plan. We'll say, okay, we will encode it this way. So then I encode and I send them the ciphertext. They then decode it and they, buy me the book. The problem with this whole scenario is that not only will an eavesdropper be able to see my ciphertext of my credit card information, they also heard the entire discussion of what particular code I'm going to use. And if Eve knows what the encryption function is, she can work out a decryption method as well. So there goes the whole idea, right? No book for me. So this is the point where we start entering into using the mathematical part of mathematical cryptography. Remember how I said there was a so-called encryption function? Well, if there's an encryption function going this way, we also expect there to be a decryption function going back the other way. And, okay, we can do this, we can do this, but maybe doing this isn't as easy. Maybe it's really easy to encrypt, but it's really hard to decrypt. This is a so-called trapdoor function. We'll talk more about specific trapdoor functions in later episodes, but here's a quick example. If I hand your computer two huge prime numbers and say, multiply them together, it'll do it really fast, in a fraction of a second. But if I hand it the product of those two primes, without telling them which primes it was, and then say, factor it, this could take a really, really long time. there are trapdoor functions used in mathematical cryptography where the encryption phase might take a fraction of a second, but the decryption phase might take centuries. So now we're in a good place. I send all of my encrypted information using a trapdoor function. So Eve has access to it, she knows how to decrypt it, but by the time she does it, well, the data won't be any good anymore. Here's the problem with that idea, though. Isn't the bookseller going to have the exact same problem? So here's where the last clever idea of mathematical cryptography comes into play. The bookseller can set up the whole system. They can tell me how I should encode my data. And when they do so, they can set themselves up a back door. They can set themselves up a shortcut, a way to do the decryption really, really fast. They won't tell anyone about that, but they'll know how to do it. This particular shortcut is often referred to as a private key. This whole system is referred to as a private key crypto system. It means that whoever sets up the system can receive encrypted messages that are encoded very, very quickly, but only the person who set up the system can decrypt them quickly. Well, anyways, we'll talk more about that in the future, but that's all for now. Bye.